Hi. Hold on, let me turn on some music so it's not as awkward. Can you hear that? Yeah, you can hear it. It should be very quiet. I could turn it up a little bit. Let's see. Can you hear that? This is also a quieter song. We'll adjust the volume as need be. But today we're gonna be I'm gonna be talking about this little CPU. It's very simplistic. We're gonna be talking about this CPU I made in Build Logic. It's a Roblox game where you can build logic. It comes with a lot of already like pre-made components like registers and EEPROMs and stuff, and a bunch of adders and a bunch of math that I didn't have to do, thank God. But this video is gonna be me writing a program to a cartridge and debugging it and making sure it works. And the program we're gonna write is just a simple little program where it's just gonna move a single little dot on this 16 by 16 matrix screen. I think right now I have is the clock started? Oh, I must not have a program loaded in. Do I? I do. Huh. Well, whatever. It doesn't matter anyway. So I'll start off by talking about what the program does and how it relates to the CPU. So the first thing we do is that we immediate to the A register just a bunch of zeros, because at the start of this program we can't guarantee that the A register is reset to 0, so we spend 2 instructions doing that. You can only immediate to the A register. There are 3 registers in the CPU. There is I'll go over there and show you. We don't have to go back to the cartridge until we're programming. Can you guys hear me? Sorry, I should have checked this before I started rambling. Yeah, you guys can hear me. Music's a little loud though. I'll turn it down a little bit. There we go. So this is the A, B, and C register, and then you have RAM over here. You can only immediate to the A register, which is why that sign's there. So we immediate this value to 0, and then we set the RAM address to that, because at the RAM address 0 is where input is taken in from this. I guess you can call these USBs. The design of these aren't very ergonomical, and I realized that only after I started wiring and circuiting everything, and I'm too lazy to go fix it. So these just have a pretty strange choice of design. But as you can see, this is the address for the controller input. Right here, it's all zeros. So whenever we go to that address in RAM, we're actually reading from the controller instead. So we go to the controller input, and then we copy the input byte, which there's 8 inputs over here, and they each respond to a single bit on the input byte. And then we copy that, whatever we're reading, into the B register from RAM, and then we immediate the value 100 into RAM, and then we copy that to C. And if B and C are equal, which B holds the input and C now holds this number, then we set A to this and put it into B. And the reason we're doing this is because if the input is left, aka this is the only bit turned on, which this bit corresponds to the left on the D-pad right here. If that bit is on, then we set B to a different value, because what we're holding in the B register is the value we want to add to the dot in order to move it on the screen. Because this matrix, this 16 by 16 matrix works by starting at 0 and going left to right, up to down. So it starts here at 0 and then goes 1, 2, 3, 4 all the way to 15. Starts at 16 here and then goes all the way, so on and so forth. You start at the top, you read down, and you go left to right. So we put this here and we put that into B if the input is left, and then if the input is up, which is this one, which we copy into C, and then we compare the two, which again in B is the input byte and in C is this number. Then we actually want to copy this to B, and then we're going to save that into the offset is saved into the B register. So now we go to the character position register, or the character position address in RAM, and then we copy 2A from RAM. We copy the character position, and then we add the operation. I should probably talk about the operation instruction. This is the entire instruction set. It's incredibly simple, but the operation A and B into C, and since we'll add A and B, and then the output will be in C. So we do that, and then if B and C are equal, then that means there was nothing in the B register. There was nothing in the B register to be added, and we set A to 0, and then we jump back to A, which is 0, which means we jump back to the start of the program and run it again, checking for input. And then if something did happen, this will be skipped, and we copy to RAM from C, which now holds the offsetted value, and now we put that into RAM, which is the character position, as that's what the address is set to here. We copy that to RAM from C, which holds the output from the operation. And then the rest of this is just going to the different, I guess you can say USBs, and setting very specific values. Like you set one to reset the screen, which is on this one the 8th bit, or 7th bit if you're going from 0. And in this one we go here to set the clock signal, which I'm pretty sure is also the 8th bit, which I think is what's pulsing right here. So cool. And then, so let's step through it. We go to the address that has the reset USB plugged in. Each USB takes up an address in RAM. It goes to this specific address, and then it puts this into RAM, which is copying it to that USB. And then we go to this specific address. We copy this into RAM, which is pulsing the clock. Then we set A back to 0, and then we put that into RAM to turn the clock back off. And then because A is already set to 0, we can just jump to A without using another immediate instruction. So that's the entire program. It's only 46 bytes, which might not be much, and it isn't, but ooh, excuse me, sorry, I'm burping like crazy. You only get 255 bytes per cartridge, so it's not the most advanced computer by any means. You could probably deduce that by this very, very simplistic instruction set where two of the opcodes aren't even used. So we're gonna write the program into this cartridge right here, which I've already labeled. It's clear. I made sure it was clear. Let me check again. Yeah, there's no data stored in this. That's the address of where you're writing in the cartridge, and that's the data inside. Index back to 0. And I guess we could just get started. So the first thing we do is we immediate the last 4 digits to 0, And oh wait, I'm setting the index instead of incrementing it. We set the last 4 digits to 0, and then we set the first 4 digits to 0. Then we set our RAM address to that. Sorry, if I don't keep track of this program, I'm gonna lose where I was and skip instructions. Set RAM address is 0, 1, 0. And we set our RAM address to A, so none of these need to be touched. And then we copy to B from RAM, which is this instruction, and you copy to A, B, C, or RAM from A, B, C, or RAM, which is why they're written like this. I'm pretty sure this is the wrong order of the prepositions there, but English is dumb anyways, so who cares. Copy to B from RAM, and then we immediate the value 1000 to the last 4 bits, so this bit is off. Over here, I'm going to highlight this instruction so I know where I am. This is the instruction to immediate to the A register. If this wasn't tagged, you'd see that it says the first or last 4 bits. If this is on, we write to the last 4 bits. If it's off, we write to the first 4 bits. And the bits not being written to at that time will just remain unchanged. And now, did I already put this instruction in? Let's find out. Well, there's no instruction there. Is there an instruction here? Yeah, it's to put in the instruction. So let's increment by 1 and then start updating data again. So now we want to copy to C, which A, B, C from A, and then A is 0, 0. And then update that data. And then if B is equal to C, which I just remember because that's a pretty pattern, but if we go over here, this is the flow command, which was really simplified actually. It's just these two arguments, and then all of these commands if it's an if statement. This says if C is equal to 0, if C is not equal to 0, if C is equal to B, and then so on and so forth. So we want this one because we want to check if C is equal to B, or B is equal to C. I wrote it here. So we write that instruction. And then we, sorry, brain fart. We immediate the value 1111 to the last 4 bits. And then the value 1110 to the first 4 bits. And then we want to copy to B from A. Okay, and then we want to end that if statement, which I'm pretty sure is this, but let's go check. Yeah, end if is just that last bit turned on of the flow instruction. Then we immediate the value 0. Yeah, we need to do this because this could have ran and it would have messed with the A register. I was checking to make sure we actually needed this instruction, but if this ran, then it would have messed with our A register and we would need to reset it. So if A is equal to 0000, or wait, we immediate 000 to the last 4 bits, and then 0010 to the first 4 bits, and then we copy to C from A. Then if B is equal to C, which is this little fun, I'm gonna go check because I get nervous every time. Yep, C is equal to B. If B is equal to C, or C equal to B, Then we actually want to mediate the value 1110, 1111, and then we want to copy to B from A. Then we want to end that if statement. Then we'll immediate the value 0000 to the last 4 bits. Then the value 0001 to the first 4 bits. And we want to set our RAM address to A, which I don't remember the instruction for. It's this one. And then we want to copy to A from RAM. Then we want to do an add operation, which is this one right here. And then it's just the last bit. None of these bits need to be on. It's only this bit. And then we want to copy to B from A. And if B is equal to C, we want to immediate the value 0000, 0000 to the last 4 bits 2. Sorry, brain fart again. And then we want to jump to A. Let's highlight where we're supposed to be. Wait, sorry, I completely forgot the instruction. Jump to A. Then we want to end that if statement, which is that. Sorry, I'm just staying quiet. I'm focusing, I'm thinking. I apologize for the lack of commentary. I also don't know if this microphone is a really fun thing where if I'm like 1 inch away from it, it's insane. It's much more quiet. So I'm sorry if you haven't been hearing me this entire time. We just ended that if statement. We're here. So we're going to copy to RAM from C. So A, B, C. And then this would be A, B, C, RAM. So then boom, and now we're in setting random bits on and off. So the first 4 bits, or the last 4 bits, 0000, 0011, or 0011. Set our RAM address to that. Let's go check to make sure that's the right instruction. Yeah, it is. I'll always forget that one apparently. And then because this is a bunch of mediating in the same instruction over and over again, we have to very particularly highlight this just so I don't forget. The last 4 bits is equal to 0000. Copy to RAM from A. Immediate the value 0000, 0010, and set a RAM address to A. Then immediate the last 4 bits with 1000, 1000, 0000, and then copy to RAM from A. Then immediate the last 4 bits with 0000, then copy to RAM from A, and then jump to A. I think the music's a little too loud. Sorry. And then the jump instruction is just that one. So jump to A. And now our program is finished. we finished writing it, but this has had a problem before in the past where it just doesn't write. So let's actually step through each instruction and see if it lines up with what we have in our document. I'm going to save this. So let's increment by 1 without updating data. We have to remember to turn that on if we want to overwrite anything. So we mediate the last 4 bytes with 0, 0, 0. Then the first 4 bytes with 0, 0, 0. Then we set RAM address to A. Then we copy to B from RAM. Then we set the first 4 bytes to 1, 0, 0, 0. We copy to C from A. That's right. And then if B is equal to C, then we want to immediate the last 4 bits with 1, 1, 1, 1. And then the first 4 bits with 1, 1, 1, 0. And then we want to copy to B from A. And we want to end that if statement. Then we want to immediate 0, 0, 0, 0. Oops, sorry. Oh, fuck. 0, 0, 1, 0. And copy to C from A. And then if B is equal to C, immediate 1, 1, 1, 0, 1, 1, 1, 1 to A. And copy to B from A. And then end that if statement. And then immediate 0, 0, 0, 0, 0, 0, 0, 1 to the A register. Set our RAM address to A. Copy to A from RAM. Do the add operation. Copy to B from A. And then if B is equal to C, immediate 0, 0, 0, 0, 0, 0, 0, 0, and then jump to that instruction, and then jump back to 0. End that if statement. Copy to RAM from C. And then A is equal to 0, 0, 0, 0, 0, 1, 1. The address is equal to A. A is equal to 1, 0, 0, 0, 0, 0, 0, 0. The address... Ooh. Oh, sorry. Copy to RAM from A. Oh, you know what? We never, hold on. We never we never turn off the reset signal. So let's do that. This is the copy to RAM, or this is copy to RAM from A, and then A equals 0, 0, 0 again. So we can copy to RAM from A again, and this time turn the reset signal back off before we turn on our clock signal. So we're copying to RAM from A for the first time. We're here, and we need to add a couple of instructions. So copy to RAM, and then we want to immediate 0, 0, 0, 0, and then nothing else, which this program isn't going to do because we have to fix it. 0, 0, 0, 0, we just did this, and then we want to copy to RAM from A. And now we don't need this, so we can underscore it to say that we don't need to waste an instruction doing that. And then we can go to here. So we just copied to RAM from A. Let's increment by 1 again. And then we want to immediate. These are going to be right anymore. We're starting from here. We want to immediate 0, 0, 1, 0 to the last 4 bytes. Then we want to set our RAM address equal to A. Then we want to immediate the value 1, 0, 0, 0, 0, 0, 0, 0. Then copy Oh, sorry, I lost where I was. Copy to RAM from A. And A, the first 4 bits are 0000. Then we want to copy to RAM from A. And then jump A, I think we're at. Which is, oh, the last 2, or the first 2. Or the leftmost 2, sorry. So, all in all, let's go back to 1, 0. We could just go back to the beginning. Don't update any data. Let's just set this immediate 000 address equals A, copy to B from RAM, A equals 1000, copy to C from A, if A equals that, copy to B from A, in that if statement, A equals 0000, 0010, copy to C from RAM, or from A, if B equals C, 1110, 1111, copy in that if statement, 0000, address, copy to A from RAM, add, copy to B from A, if 0000, jump to A, in that if statement, copy to RAM from C, A equals 0000, address that, 1000, 0000, copy to RAM from A, immediate 0000 to the last 4 bits, copy to RAM from A, 0010, address 1000, 000, copy to RAM from A, 0000 to the last 4 bits, copy to RAM from A, then jump A, and then nothing else, right? Yeah. So let's save our EEPROM. I like to click it a couple times just to be sure. And let's put it into our computer and see what's happening with it. So now we just have to select the cartridge, which kind of is it's a little tedious to do. And then we move it. All the way over here. I like to have a block of separation so I can see it happen. And then we click enter. And oh, I forgot to move the sign. Shite. Well, now there's a sign over there that says moving character. Let's move it too. Get over here, you. Oh, deselect. Put the sign where it belongs. And put it here. And now we want to load that into our computer, which I'll try and show you what's happening. As soon as I click this, a bunch of lasers start flashing. This is the cartridge communicating with the computer through lasers. It's so you don't have to wire up all the components that you want to communicate with each other, and you could just move things where they need to be. And now it's stepping through every single address to add it to memory. Oh, I kept the computer running while we were doing that. Oopsies. Let's reset our computer, and I guess we can just load it again. let's reset our prom and then let's load that again from our program. Okay, now the computer isn't running, and you can see the program being loaded in the computer until it stops. It's gonna load in all 255 bits, even if the instructions stop. Maybe there's a way I could fix that, but for now it's kind of just gonna read the entire thing. I'll definitely need a way to fix it if I'm gonna upgrade to 16 bits, because the 16-bit EEPROM has way more addresses, and it'd be way too long if I just tried loading through every single bit. Or maybe I need a faster way of communicating besides these lasers. Whatever the case may be, our program is now loaded into our computer, and let's see what happens if we just run it. I'm doubtful that it'll just run the first time. Let's just get going. Computer is now running our program, and it's stuck. How strange! It got stuck at an instruction. Why is it stuck? Well, what's this instruction? It's the end if statement. It's one of these end ifs. I'm assuming it's this one. No, it could definitely be this one. So, what happened? Let's figure it out. Our opcode. Where's our opcode selector? Is this our opcode selector? No, that's an 8-bit multiplexer, you moron. Where's our opcode selector? There it is. So this is our opcode, which goes to this, which powers this multiplexer, which chooses this value instead if the let's actually talk about the ifs and the end ifs, because that makes this CPU pretty unique. While we have a different program read-only memory, we also have another one that saves the addresses of end if statements if the condition isn't true. So that way the program knows that if this isn't true, I need to set myself to this address. What I'm assuming happened is that it didn't work, obviously, but I'm curious why. So now we're selecting this one because this is on, which takes input from this opcode, and make sure that this condition isn't true. So and this condition isn't true, and the condition we have chosen is whether or not C is equal to 0, which is strange. Hold on a minute. Because this is a C is equal to 0, right? It is. Did I write the program wrong? There should be no C equals 0 in here. Well, this might be returning true because this is loaded. This is from these three, and then that chooses that by default. And because it's this opcode instruction, and this is just not true at the moment, and there's, I guess there's an, oh yeah, there is an address here, which we set, or we pulse if we're reading from a program, or this opcode is selected, and this bit is not. But this bit is not. We can do a rough patch and just say that if this and that and not later, and we're not ending the if instruction, which in this case we are. So let's delete this and move this down. Oops. Because we're ending the if instruction, we don't want to set the address to anything. So not, and then instead of this, we'll attach this. Hopefully I didn't break anything, but we can honestly just reset the, oh wait, where are the pipes? Poles, that's what they're called. I just need a pole and then a corner pole, so pole, oop, wrong key again. There we go. So let's stop the computer from running and just restart from the beginning and see if anything appears on the screen. Our program should still be loaded into the computer. This might take like hours upon hours. So now we have loaded our program. Things are happening in these registers, specifically this A register. You'll see it change a lot. But I think it's skipping if there's no key being held down, which we can check by going to this address. And this address is 6 bits long. And I'm pretty sure the one over there was only 4. There's an airplane flying over. I'm sorry if you can hear it. Yeah, this one doesn't 1, 2, 3, 4, 5. This one only goes up to 5 before it restarts back to 0. So let's see what happens if we just stand on a pressure plate. Now it could either be taking a really long time or not working. Whoa! Something was there. I'm so curious. Okay. So this is the character position chip where we save the character position and input it into the screen. Let's just move this over here and play around with the computer some more. So it is incrementing by 1, and then this will set it. Whoa, what the hell? Oh wait, it wasn't finished. Whoa, that was weird. And then it'll go back to 0. There was something on the screen for a moment. Oh. I'm gonna guess that these are not updating when they need to be. So what I'm gonna do is that I think the lasers are just kind of slow, and I'm gonna bump down the computer's speed a bit and see if these lasers return the information. But we're not gonna see it because I need to be on a pressure plate. Let's move our input closer to the USBs so we can see. Yeah, see, it's doing it over there. So it's sending it to them. But now this computer runs a lot slower. I'm not gonna speed this up. I don't want to edit this footage. Who would? Let's see, does it update the clock signal? There, pulse the clock signal. Pulsed it again. And this is the reset. Yeah. Maybe, I wonder why it's not working. I also wonder why it's playing with this register. Is this updating at all? Yeah, no, it is. Curious. Well, let's look at the screen. Just watch it for a while. It doesn't seem to be working. So all of these are off, and all of these are off, and this is off. So let's go over to our test screen over here. See if we can figure out why. Maybe it's a problem with the screen. Let's just set our character position to 0. Make sure we're in set position mode. Set the character to 0 and the color to 0. And then let's pulse our clock. But if we set our position to 1. Oh, now we know. If there's nothing selected, nothing gets drawn. So we need to at least set maybe a character or a color. Oh, those are the last 2 bits, sorry. So, I think we're actually in luck because I think, let's see, which one of these corresponds to color? It's our reset, or it's our clock signal. So, whenever we go to address 10 right here, we can just update these instructions to include colors too, which the colors are just the first 6 addresses. So if we set them all to 1, then it'll be a white little dot. So 1111 10 11. And now we'll pause that to that, and then 0, 0. Well, we actually don't need to keep this. Let's actually set this to 0 so that way we can stop the clock again. So we need to do another instruction to set this back to 0 too. Then we copy to RAM from A, and then we jump to A. So this program is already running, and we know that it works somewhat. I'm pretty sure it works. We'll see if it works by putting the cartridge and changing the colors. Oh, am I not selecting? No, I'm not. I will say that selecting these cartridges is probably the most annoying part of making anything in this game. I could have come up with a better system, but I did it. Take it. Why am I not selecting anything? Oh, because I have the data mode selected instead of select mode. Oops, sorry. Did not mean to select you. And now we have majority of it selected. Not the sign though, I always forget the sign. Let's take you back to our programmer. And fun fact, if you want to subtract from a number, you can do the so if I want to add one, but if I want to subtract one, I could just do the opposite of 1 in bit. So I go 1 1 1 1 1 1 1 1 0, and then we increment by that to go down. So let's go until we reach the A equals 1 0 or 0 0 1 0. This is the jump, copy to RAM. This is a mediating 0 0 0 to the last 4 bits, but it won't to the first 4 bits because we didn't have to before. So we're copying to RAM, and we're copying. Oh, we're copying to RAM, and then we were jumping. I think I don't remember. Let's just get back to where we're supposed to be. 0 0 1 1. Did we go all the way back up here? Well, let's find out. 0 0 1 1. And we set RAM address to that. We mediate 1 0 0 0 0 0 0 0. Copy to RAM from A. Last 4 bits are 0 0 0. Copy to RAM from A. And then 0 0 1 0. Address is equal to that. Then A. Let's update our data. Stop incrementing just for a little bit. A, we want the last 4 bits to equal 1 0 1 1. And then update that data. Increment. And then 1 1 1 1. And then we want to copy to RAM from A. Then A equals 0 0 0 on. Oh wait, I wasn't. Oh shit, I was updating data. Uh-oh. I didn't mean to have the update data switch on. Let's go back. One zero zero zero. Oh wait, did I do it right? 1 1 1 1. Increment by. Yeah, we're here. So then we want to update data and immediate 1 1 1 1 1 to the first 4 bits. Then this is the instruction I messed up, I'm pretty sure. copy to RAM from A, and then A is equal to 0, 0, 0, 0, 0, 0, 0, 0, copy to RAM from A, and then jump to A. And I'm pretty sure all of that's correct. So let's save that EEPROM one more time. And then we can remove our cartridge from the programmer. Oh, it's already selected. Beautiful. Then we go here. Put it right here. Enter. And let's stop our computer from running. Let's move our controllers back here. Oops. No, we can move it. Let's move it farther away from the cartridge holder. And we'll keep that register there just in case we want to see. We'll actually drag that too. Am I still recording? It'd be a shame if I wasn't. Yep, we're still recording. Then I'm going to load it into the computer. It's loading in right now. And then we'll play it whenever it's done loading. I'm excited. It was working pretty well. I honestly didn't expect it to. I hope it draws something onto the screen. I'm pretty sure. Did I reset the? No, I need to reset the registers. Now our registers are reset. We are reading. We have finished our instructions. Let's see what happens. Yikes. Uh-oh. Nothing's working. Let's start playing around. Oh! Move, my glorious dot. Go! Yes! I don't know why the color's weird, but who cares? It's orange, I guess. And then if I get off of it, it should stay there. I want you to move down, my glorious orange dot. Please move down. Yeah! I did it! Now go here. Do it. Go, go, go. Move, my orange dot. No! Why did it do that? Oh, it's going like down weird. Oh, maybe it didn't. These are kind of like faulty, I'm pretty sure. Oh, you know what's happening? It's going. Oh, wait, did that work? It worked for like a second. Yeah, it's working now. Because then it goes from here. Oh, it's going like 2. It's skipping 1. Strange. I must not have added the right bit. But if I go up, will that work? No, it also skips 1. These are the 2 we're checking with the if conditions. Okay. So that's the wrong bit. Like, I'm not supposed to be doing that. Well, That's strange, because I feel like if I just add 255, all of it's going to do is just reset. Like, hold on, let's test it. Adder. We'll do dip switches. Pew, 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 pew. If I just add these together, huh? I'm now realizing something about the adder. It only goes up to 120. Well, that's because if I were to switch this all on, and I just wanted to... Oh, so it is supposed to be that. So this is supposed to be 1111111. Because that's definitely one less. And then if I were to do all of these, it would just turn that last bit off. So this is supposed to be 1111111 to subtract 1. And then we want to subtract 16 in order to move it down, or move it up, sorry. So 16 is this bit, and if I wanted to subtract it, I go boom, 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 boom. And then let's say I wanted to subtract 16 from 64. Let's pull out a calculator and see if that's right. First off, let's sanity check. 64 minus 16 is 48. So 32 plus 8 plus 4 plus 2 plus 1. Oh goodness, it's 47. That'd be an odd number. So what we need to do is we need to negate it, and then we need to, because the bit doesn't start at 0, it starts at 1. It doesn't start at 0. Or maybe, I don't know, I think I'm just making things up. So what we actually want is this, which is 32 plus 16. So this is 64 minus 16. Oh, wait, where's my calculator? I put it away for some reason. So 64 minus 16, because I'm stupid and don't remember anything, is 48. Then 32 plus 16 is 48. So we actually want to oh shnikes, I'm editing more than I meant to. So we actually want to instead of doing 111000, we want to do 11111 and 0000 apparently. And this will subtract. Let's try it with another number. 128 plus 64. Oh, I keep getting rid of the calculator. 128 plus 64 is 192. Minus 16 is 176. And 128 plus 32 plus 16 is the same number. So this is what we want. This is the offset we actually want. So we can honestly just step through our program again and rewrite it with this. So let's grab our cartridge, which is still annoying to do. I'm honestly surprised that it works so well, though. I hope you heard my excitement whenever I was reacting. Oops, sorry, I had some other stuff selected. Ooh, I almost got it first try. Oh, was I stepping on the pressure plate? Interesting. I hope it's selected. Oh, I didn't select one stair. And then don't forget the sign. And now let's go over to our thing, and let's just start over from the beginning. And let's just go through, and then whenever we encounter an instruction, we just fix it. So let's go here. Let's go to 0 without updating the data, which we'll go through again. 0000, 0000, set the address, copy to B from RAM, 1000 to C from A. If B is equal to C, we want to do 1111, 1111. So this will stay like this. Let's stop incrementing. Let's update the data. This will be 1111. And then let's start incrementing again, turn all of this off, and stop updating data. So 1111, 1111, copy to B from A. In that if statement, 0000, 0010, copy to C from A. If B is equal to C, then 111, or we want to change it now. 1111, don't increment, update data. 1111, and increment without updating, we can update. Let's just turn it off to be safe. 1111, 1111, sorry. 0000. And we need to update that data. And then don't update any more data. We copy in that if statement 000001, and the rest of the instruction, the rest of the program continues. Save our EEPROM. Let's save it. Make sure we don't lose all of that. And let's put it back in our computer. It's already selected too. Beautiful. Do 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 do. Okay. It's in. Oh wait, it's off by 1. Shoot. That would have been horrible. I bet the instructions would have been all mangled. Boom. Okay, perfect. And now let's stop the clock. Reset everything. I'm not sure if this resets the screen. I don't think it does. We'll reset our prom too, just to be safe, I guess. And then we will load in probably our final iteration of the program. And then we'll be done. And then we can play it. So we'll wait for it to load. It takes a while to load, honestly. We're over halfway through though. You can tell because that bit's on. And I'm just waiting. I don't know what to talk about. Okay, it's done. Let's load in our program. I don't think anything's gonna happen until we step on the pressure plates, because it doesn't update the screen until there's input. I don't know why I didn't think of that. Now they won't show anything until somebody's touching something. But let's start the clock and let's go left. Oh, it started down there. Oh, it probably read my other input. So now we're going left. And let's just go left a little bit before we test the two controls that weren't working. Now let's go up. Was it going up? I wasn't. Oh, wait, hold on. Okay. Yes, it goes up. And then we go left. It's slow. Yes, it works. I made a dot move on the screen. Let's see if we can make our computer even faster, because I did this because I thought the USBs really, I'm pretty sure the lasers in these laser detectors, which is how it communicates, aren't the most. Oh, Beagle Gorp. I don't Beagle Burp. I'm pretty sure these aren't the most reliable things. I don't even know if you could see that. OBS is kind of like Discord's kind of magical where it just doesn't appear on OBS. I don't know how it does it. So I don't know if you saw that or not. Okay, but now the computer is running 5 times as fast. So let's see if it works. Oh, did it do that? Go. That's so fast. Oh, why was it going up? Please tell me it was just like, okay, I think, yeah. Whenever you have a higher speed, you introduce some artifacts between the lasers. And so it's not guaranteed to work. Cause see, I see sometimes it's green. Oh, and sometimes it does that. What the hell? You can't trust the computer when it's going too fast because I think it's the lasers. Oh yeah, look at that. What's happening? Well, it works whenever we're slowed down a little bit, so we'll just stay slow. Yeah, it takes forever now, but we should be moving normally with a consistently orange dot. Awesome! We did it! It was all by this little CPU. Everything, there's no like hidden, this is entirely what's running it. You can see it working right now. All of this is running my little program I made that moves a little dot around on the screen. Nice, we did it. I don't know. I guess we end here, huh? I guess our journey stops now. We finished. This is a world on build logic. I'm pretty sure I said that at the start. This is a build logic world that I made. It works. I'll probably have it on public servers sometimes if you want. I like showing off my little computer to people, so it's fun. So maybe I'll be on there if you check, but I'll link it in the description. I'll also link the Spotify playlist I'm using as background music if anybody wants to listen to that. Thank you for watching. I think we're like an hour and a half in. No, we just reached over an hour, but it works. Oh, it's white now. Why is it white? Go back. Go back. Go back. No, it's not white anymore. So there's still like very few artifacts whenever it's running at this speed, but it's much rarer. Okay. So yeah. Now we know. Thank you guys for watching. This is a little avatar. He's cute. He looks nothing like me. I don't even wear glasses. Thank you guys for watching. This is this hour-long tangent. I appreciate it, and I will see you when I see you. I don't know. I don't have a consistent uploading schedule, especially to this channel. I'll see you guys when I see you. Oh, happy 4th of July. That just happened. Bye.